All right, so we'll talk about some use cases and example methods. And by the way, I'll keep us at the 3 p.m. break. So we'll still have time for our 30-minute break. So when we're thinking about, okay, within all of the things that are important to work towards with what Catherine presented in terms of what we can monitor in the world of agriculture and food security using Earth observations data, what's interesting in terms of remote sensing data, and what's interesting in terms of AI, including many topics in machine learning generally and computer vision. Kind of the core topics at the intersection of those are what I'm going to talk about here. So this is not an exhaustive list by any means, but these are really like the main tasks that people are working on at the intersection of these 3 fields right now. So these include crop mapping, crop type mapping, field boundary delineation, yield estimation, and pest and disease detection. So there are other kinds of things that people are doing. For example, detecting farming practices. Maybe you want to detect if there's irrigation happening, or you want to prescribe irrigation at the field scale, or you want to map soil types, et cetera. But those are still like fairly small research areas. So these are kind of the core ones that we've listed that we feel have kind of the broadest impact across this space. And a lot of these other types of methods, like those I mentioned, also map to similar kinds of problems that we would use to solve these. So for example, crop mapping and detecting whether something is irrigated or not is just binary classification. Crop type mapping is multi-class classification. Field boundary delineation, we're doing segmentation. Yield estimation, we're doing regression. Pest and disease detection, we often treat as an anomaly detection or out of distribution detection problem. And so within all of this, using the fact that we're using remote sensing data with all of these nuances that I described before means that we have a lot of interesting other research problems within domain adaptation, distribution shifts, multi-fidelity data fusion, how do we learn from limited labeled data, all of these different topics that we can study in the context of remote sensing data and agricultural applications. So I'm just going to go through each of these topics here and describe what it is, and also 1 or 2 example methods that are being used to address that task. So crop mapping, again, is just mainly binary classification of pixels, either as crop or non-crop. Sometimes you might also see this as what's called land cover classification, which would be classifying multiple classes like water, buildings, agricultural fields, forests, et cetera. But usually when we're talking about crop mapping, we're talking about this binary setting. So we input some satellite data and out we get a classified map of that data where we're distinguishing between pixels that contain cropland or do not. This is an example from China. And so one example that we've worked on in our group is shown here. So we had a project where we wanted to classify cropland in Togo, and more generally, we use this approach for classifying cropland everywhere in the world, in particular where we have limited labeled data in a given region. So the way we do this is we have a very large data set, which contains global samples. So we have in our crop harvest data set that I mentioned before, we have over 90,000 labeled examples globally distributed of crops and crop types. But within a particular region, such as Togo, a country in West Africa, we might only have 40 or a couple of hundred labels, very much smaller data set. And so how do we use these data sets together in an efficient way? So the way we do that is we have a multi-headed model, which in this case, is an LSTM, but it doesn't have to be an LSTM. You could use different types of architectures here. So it's basically a multitask learning setup where we have two outputs, one path that's taken for the global distributed data and one path that's taken for the local data. And so the model takes in a 12-month time series of Sentinel-2 satellite observations at all of those label locations in all of these spectral bands that Sentinel-2 provides, and outputs whether there's a crop in that location or not. And we encourage the model to learn from the global data set, but specialize its features that it's learning more towards the local data set by using a loss function that penalizes the model more for getting local samples wrong. So if the model gets one of the Togo samples wrong, it's penalized more than if it's an example in China. And using that model, once trained, we applied it over the entirety of the country of Togo to create a map like this one shown on the right of cropland in Togo. So crop type mapping is similar, but here we're classifying every image or pixel location, generally a pixel location, into one of N crop type classes. So maybe in this example, this is the USDA cropland data layer, which is a random forest result. There's classes of corn, soybean, sweet corn, alfalfa, wheat, water, all kinds of things that it's like, I don't know, over 100 crop types that are growing in the US that are available every year in that map. So that's the kind of result that we're trying to get. We input the satellite data and now we get a prediction of one of N crop type classes. So one example of this is this paper, multi-crop classification in Ghana and South Sudan by Rose Rustowitz when she was at Stanford, where they, this is super small, sorry about that, on the right side. But what this is showing is basically three kind of units with convolutional LSTM units in taking in 3 different satellite data sets. So it's taking in planet data, which was that high spatial resolution, daily cadence data set, plus Sentinel-1 data, which was the synthetic aperture radar one, and Sentinel-2 data, which is the optical 5-day revisit one, and processing all of those through individual units, and then joining the features extracted by each of those at the end of the network to make a final prediction based on all of those satellite data sources of what the crop type was in each of those pixels. So here we actually have a segmentation output, but in a lot of cases, this is done on a per pixel basis too. And I'll show you an example of that as well. So you can see here are some input examples. So they've taken these little patches of much larger satellite images, and they obtained these target labels, which are where these different crops are in the fields, and then compared several models, including their own and a random forest, always a surprisingly competitive baseline for classifying those multiple crops. Another example, crop type classification can sometimes also be posed as a one versus rest binary classification problem. So this is especially useful when you're trying to build a model that you can use for classifying crops that you might not have planned to classify. So maybe in this year we have banana, maize, and soybeans in our data set. But then next year we get some data for wheat. Well, we don't want to have to completely retrain our model to have all of the output classes, really like open set classes here we want to, an easier way to do this would just be to do one versus all. So we have a separate model for each of the crops. This is what a lot of people do operationally. So one approach that we've done for this is called task-informed meta-learning, or TIML. So the idea here is that this is a variation on model-agnostic meta-learning that enables context between tasks to be learned by the model, which is especially important for our geographically defined tasks. So our tasks in this data set are classifying different crops in each country. So one task might be maize versus rest in Kenya, another might be wheat versus rest in Ukraine. And so here we're able to learn, using this approach, we can learn, for example, that classifying crops in Kenya is more similar to classifying crops in Tanzania than it is to classifying crops in Ukraine. So this provides a way for learning context between tasks when we have this metadata, any metadata available at the task level. So in this setup, we have a task encoder that takes some task-specific data, which in this case is the location of the points, so the latitude, longitude, as well as the category that we're learning. So whether if it's a cereal type of crop, a tree type of crop, some metadata that we have at this task level. And then we encode that task vector using a separate network. And then that is used to modulate the hidden vectors of our model, which in this case, we use the same model that I showed in that Togo example, that LSTM, but could be used for any model where you have gradient-based training. So, or where you would use meta learning and where you have task level information. So kind of the intuition for this is that TIML enables us to push the weights of the initial weights learned by mammal in a direction that's closer to the optimum for each task. So this modulation is applied before the task fine tuning even begins. So it's kind of nudging the weights closer before it starts to fine tune, and hopefully learns more efficiently, gets closer to the optimum weights for that task by having this prior from the task level information. And so using this, we've shown pretty substantial improvements to other baselines for crop type classification, as well as compared to just using vanilla mammal. So the next one I'm going to talk about is field boundary delineation. So this is segmenting the individual boundaries of crop fields, or you might also call them parcel boundaries. So that looks like this example here, where we have a satellite image and we want to identify a polygon really for each of those individual fields. So this looks a lot like an instance segmentation problem. One example of this is from a paper by Sherry Wang and co-authors published this year, where they built a model for field boundary delineation using transfer learning and weak supervision. So the idea here was that because you don't have a lot of labels in some places, but you have a lot of labels in other places, similar to the Togo example I showed, you want a way to make as much use as possible of those large available data sets to help you learn more efficiently from your small labeled data set in your region of interest, which in this case was India. So in this use case, they had a very large data set of field boundaries in France that's published every year by the French government. It's like the boundaries of every single field in the country, a huge data set, really high quality, really densely labeled. In contrast, they had some pretty sparse and sort of randomly distributed, not completely labeled regions of field boundaries in India. And so they basically pre-trained a model on the labels from France and then fine-tuned that on the labels from India, but also do some other fun transformations to make the images from France look a bit more like the images from India by using different data sets with different resolutions, since the fields in India tend to be much smaller than those in France. And so another component of this, and this is actually pretty common with remote sensing data sets, is we need to use weak supervision. So if you have an image where for your training data set and you only have one of 30 fields in the image labeled, well, we don't want to label all of the unlabeled ones as not fields, or you know, have the model learn that those are negative example. So we use weak supervision to basically mask out the pixels in the loss that are not labeled. And they use a model called fractal res unet, which includes a self-attention layer, skip connections, and an encoder decoder architecture. So another common task is yield estimation. Probably something you saw a lot of in Catherine's talk is people want to know how much food or how much crop volume is, or crop weight is this field going to produce at the end of the year? And what is that aggregated estimate going to be over an entire county or country? So yield estimation is just estimating what that harvested amount is going to be per unit area. So this would be expressed in units of, for example, kilograms per hectare or bushels per acre in the US. Or in this case, tons per hectare. So this is showing an example yield map of taking all the satellite data over the entire US and producing a map of the yield in multiple years for maize fields in the US in this particular paper. So one method that I'll give as an example that has been designed to solve this problem is from Yu et al. In 2017, it's presented at AAAI, called Deep Gaussian Process for Crop Yield Prediction based on remote sensing data. So their goal here was to predict the county scale yield. So they weren't trying to predict in every single field what the yield was going to be. They wanted to predict in every county in the United States what the yield would be based on the remote sensing observations. One challenge with that is that if you were to take all of the pixels in an image of an entire county, this would be an enormous image, right? So this is way too high dimensionality to use as an input to the model. So we have to reduce that in some smart way. So the way they did this was by creating 3D histograms that they used as input, where these histograms, or the 3 dimensions of these inputs were the spectral band. So they here in the top left is showing, it's really hard to see for you guys, sorry, but each row is the histograms for a particular band. And then they have those over time and also binned into spectral reflectance bins. So we have histogram for every point in time and for every band. So that gives us this 3D input. And then they use that with 2 different architectures. So they evaluated using an LSTM and a convolutional neural network architecture implemented with a Gaussian process component to try to explicitly model these spatiotemporal relationships, and did a pretty good job with estimating yield. Recently, we also took this same data set that they use and we evaluated this task using the TIML approach, task-informed meta-learning, that I showed a minute ago for crop type classification, just to show an example of using that approach with a different architecture and kind of entirely different setup, different task, a regression task rather than classification. We showed that using TIML, we could get better performance than the prior methods using the deep Gaussian process with both the LSTM and CNN architectures. So here, this is showing their LSTM with the Gaussian process, with MAML and with TIML, and then the CNN with the same. And so again, adding this context information that we have available about remote sensing data and how they relate to each other, how these examples relate to each other can help us learn more efficiently from those data, which is not something that we often have with this metadata for computer vision data sets typically. So that's another, I think, exciting aspect of remote sensing data. So finally, looking at pest disease and generally what we would call hotspot detection, meaning things that like we don't want to be there. I think Lorenzo had a presentation yesterday talking about weeds are just things that humans don't want to be there. So this is the kind of thing that I'm talking about detecting here. So detecting in-field anomalies generally that represent some unfavorable condition as defined by humans. And so an example of that here is, this is a high resolution image from a satellite called SkySat from Planet Labs, which used to be owned by Google. And SkySat used to be owned by Google. And you can see there are these kind of bare spots within the field that are actually where downy mildew disease is growing on these Chardonnay plants. And so on the right, this is showing the anomaly score from one of our models that is detecting where in-field anomalies might be. So the bright yellow pink pixels are showing higher anomaly scores and the darker ones are lower anomaly scores. And the way we did that is using a method or really a toolbox that we've developed called DORA, Domain Agnostic Outlier Ranking Algorithms, which is a package that combines several different outlier detection algorithms and makes it really easy to apply them and compare them to different types of data. So in that we have some kind of traditional distance-based methods like the Reed-Shawley method, PCA, isolation forest, negative sampling, which is a method proposed a couple of years ago, probabilistic autoencoders proposed like just last year, and some different baselines, and also includes some tools for visualizing and evaluating and organizing the outputs of those. So this particular output on the left is actually from local RX, which is just scoring each pixel based on the Mahalanobis distance between the pixel and its local surroundings. So there's not even any deep learning within that one, but within DORA, we have, for example, a probabilistic autoencoder, which involves neural networks. So this is one example of solving this task or of addressing this task. But even though this is like widely understood to be an important problem and a lot of people want this, there's still very few studies that are using modern vision or machine learning methods for detecting these anomalies within remote sensing images and fields. For the most part, what we see are studies that are using these techniques for ground-based imaging. So you might have even seen a lot of examples where it's like a farmer has a phone and they take a picture and they're like, oh, what's this disease? And somebody messages back saying what kind of disease it is, how you might treat it, or detects it, something like that. And this is great, these are really powerful, but the reason I share this example is because this is so fine scale. Like this involves like somebody being in the field, going out every day, checking what's in the fields, which can be really large areas and difficult to get to. Whereas there's a huge amount of promise with remote sensing data to be able to just immediately see these entire areas where there might be anomalies without ever having to go into the field. So using those kinds of data, we can alert farmers, for example, hey, you might want to go drive over to that area and take a look at your field. rather than them having to survey all of their fields all the time, which is extremely time consuming. So there's a lot of space for research in that task. Okay, and then I just want to make this distinction. I know I said we'd end at 3, we're a few minutes late, but I'm almost done. So a key difference here is when I'm saying mapping versus classification. Again, with classification, we're generally looking at individual samples that are treated independently, whereas when we're talking about mapping, we're talking about stitching these outputs together to make the map, which is what people want to use in the end. Okay, and then I've just listed here, I'll briefly go through some open challenges across all of these problems. And, again, we're looking at this niche of the intersection of agriculture, remote sensing, and machine learning, but these are really broadly applicable to not just agriculture. So again, I mentioned before that the algorithms and architectures that exist today are not usually designed for remote sensing data and real world challenges. So there's a lot of opportunity for designing new algorithms and architectures that work really well for the nuances of these data sets. For example, the temporal domain is often much more important than the spatial dimension here. If you look at this GIF on the right, a single input, once you put it in the size that we want for a CNN, for example, might be entirely within one of those crop fields. So, it's not going to tell you a lot about, spatially, it's not going to tell you a lot about whether that field is maize or soybean or wheat. But the temporal dimension is extremely rich in that information. I mentioned also several times, there's a lot of opportunity for improving robustness to distribution shifts, both in time and space, mitigating this training data bottleneck. So a lot of challenges in this space are stemming from not having enough labeled data. There's a lot more room for people to make their data and methods openly available. This community is great about doing that. The remote sensing community is a little bit behind in terms of openness, but that's certainly changing. We need a lot more flexible tools and processing chains for scaling these methods to be able to use them in practical applications, which I think is probably clear once you've seen these data volumes and the kind of processing we need to do. There's a lot of room for more interdisciplinary teams of machine learning researchers and domain scientists. So, looking at our team, for example, Catherine's background is in agriculture and remote sensing. My background is in machine learning, and Ivan as well. And so we can only do this kind of work when we're working closely together as a team, because we can't know all of these different aspects deeply on our own. And also, related to that, I think is capacity building and end user engagement. So there's a lot of room for, use inspired research, talking to people about what they actually want us to be doing and solving challenges to help them do that, not just working on what we think might be interesting, but might not be usable in the real world. And then finally, making models and data sets that are usable by everybody in the world. So, we can't always assume that people have many GPUs to use or any GPUs to use. And so that's really important, not just thinking about globally, but even working with rural communities in the United States. So with that, I will leave everybody to the break, and we'll be back here at around 3:30.